Okay, we are back. We had some technical hiccups. Anyway, so last time we finished the rules of equivalence. All the 10 rules are now in our pocket for usage. We discussed some proof strategies, talked about semantics and syntactic proofs, semantic proofs. Um, we talked about indirect proof, conditional proof. We briefly went over what a reductive ad absurdum is. We also did some derivations off camera, which are like just practice sessions based on the problems that we did from the Russell Marcus book. So if anyone wants to practice, we can just refer to the Russell Marcus book. That'll give you plenty of practice. Today, what we're going to do is talk about some tricks that we can, do based on whatever we have learned so far. We can have some we can derive some useful shortcuts which we can use in our proofs. uh, these are some, we're just going to discuss some of them, uh, and if I remember some additional ones, we'll just go through those as well. But yeah, so the first one is making conditionals. um, And this is straight from the book, so if anyone wants to just skip the entire thing and go to the book, that's also fine. Uh, yeah, so this is making conditionals. So we know that every conditional takes the form, can be expressed as a false antecedent and a true consequent, which just means if alpha implies beta, then not alpha or beta. So this is a rule of equivalence we learned. It's called material implication. But from this, we can derive another rule. So let's say I have some proposition P which I know is false. So not P is true. Under classical logic, propositions are either true or false. I know P is false, so I know not P is true. Now, if not P is true, then the antecedent is already true, and you can basically do an addition and attach any proposition over here. You can have like Z, and from there you can generate P. P implies Z. Because a false antecedent is sufficient to imply to make the implication true over here. So I'll just go through the proof once again because I just rushed through this. So let's start with not P. Okay. Step 2 will be an addition. Not P or Z. Remember, addition is the rule where if you have any proposition, you can attach any true proposition. You can just put a disjunction and attach any proposition, because whether or not this is true or false doesn't really matter. As long as this is true, the disjunction will be true. So you can attach any proposition over here, and so this is addition. Okay. uh, and then you can just use the material implication rule, and you have a false antecedent and you have a true consequent, so you can just derive P implies Z. That's from 2 material implication. So basically, if you have, so the trick is any from any not alpha, you can derive alpha implies beta. Similarly, if you have beta, or alpha, doesn't matter, you can derive alpha implies beta, because uh, the consequent is true, so the implication is automatically true, the conditional is automatically true. So if you have a not alpha, you can derive alpha implies beta, any random beta, uh, and if you have a beta, you can get any proposition to imply it, basically. So these are the two tricks under making conditionals. So you can make conditionals like this. There's another way to make conditionals. Let's say you have P, and let's say you have Q. This also, oh, let me write it in metalinguistic variables. Sorry. Uh, let's say you have alpha and beta. That will be alpha implies beta. You can also have, it can also mean, so this can also give rise to alpha and beta can be beta implies alpha. It can also be fine. So this is conditionals. You can do the same thing for biconditional. If alpha and beta are true, then alpha implies beta. And this, you can do the same thing for the opposite. You can have not alpha and not beta, and you can be like not alpha implies not beta. Any variation of this, okay? So those are like some tricks that you can use. They don't have a particular name. And generally when you're doing like a very rigorous proof, you wouldn't use this, but these are more of like shortcuts that you would use in just like whenever you're doing like a semi rigorous proof, where you don't want to like waste time laying out every single step in the proof. You can just take a shortcut and get to the proof anyway. So that's one set of tricks. Yeah, so let's talk about the next set of tricks. So the next one is the switching antecedents over nested conditional. Yeah. Of a nested conditional. Okay, let's say let me just change the color. Let's say you have alpha implies beta implies gamma. This is what we call a nested conditional. So it's like a conditional inside a conditional. So this conditional, this one is inside this one. That's why it's called a nested conditional. It's nested inside it. So what you can do over here is whenever you have something like this, you can simply switch the antecedents. Do you want to do a proof for why this works?
Yes, please.
Okay, so we have this, okay? How would you approach the proof?
I saw in the book they did exportation, but I'm not sure how they did exportation.
Uh-huh.
Because exportation normally you just in the book they added a conjunction after the exportation.
Right. So what's the exportation rule?
Uh, if I wrote it correct last time, it's alpha implies then in brackets beta implies gamma,
Right.
and then that's the same as in brackets alpha implies beta, and then close bracket implies gamma.
Wait a second. Is that what we wrote last time? No, that's not what we wrote last time.
And then I wrote it wrong.
Yeah. This is the exportation. Alpha implies beta implies gamma is the same as alpha and beta implies gamma. So that's what we will be using over here. We could use that, um, but you could also do it in other ways. Um, yeah, we could just do that. Yeah. So you could just do an exportation. So you'll get alpha.
What I said before, would that still be equivalent or not?
What did you say?
I said alpha implies beta, and then close brackets implies gamma.
Hmm. What do you think?
To me, it looks pretty similar, but I'll need to. That's why I did it because my it just seemed logical that it would be like this, and I didn't see that there was a conjunction.
Right.
So,
So
but yeah, I haven't. Yeah, I get to properly check it. I guess I'll need to draw out the truth tables,
yes.
right?
Yep. Exactly.
But just from my gut feeling, how I wrote it in that moment, it seemed like it was the same thing.
Mm.
Because if the yeah, I don't know.
Yeah, I guess you can try drawing the truth table and telling me next time. Um,
Cool.
yeah. Anyway. Okay. So yeah, we'll just apply exportation. And we get gamma. Okay, so that's um, exportation. Now what can we do?
Mm, yeah, let's find. Dun, dun. Commutativity.
Yes. So what's the next step?
So we can switch the beta and the alpha in different places.
Okay.
and then we do another exportation.
Exactly. Do you still see my screen, by the way?
Yeah.
Okay. Yeah. So that's QED. So yeah, you can switch the antecedents. Um, but yeah, like yeah. So that's one trick. Um, let me just move this stuff to the other side so that we can, use this part for the rules and that part for the practice. Yep. Okay. So that's another trick. So that's trick number 2, which is just like switching the conditionals. Is there anything? Oh, one sec. Let me check if there is anything else mentioned in the book. No. Um, okay, negated conditionals. Yeah. This is gonna be. This is very useful. Negated conditionals. Like I've personally used it in quite a lot of proofs. Um,
So these tricks, they are basically like rules of equivalence,
yeah,
more
sort of,
more or less,
more or less. Yeah,
because you're just replacing.
yeah. Okay. So we have a conditional, and if that conditional is false, that is the same as P being true and Q being false. Now, if I want to use metalinguistic variables, which I should, that'll be alpha implies beta is the same as alpha and not beta. So this is an easy proof. Um, so it's very straightforward. So an implication, you can just apply material implication and you can get not alpha or sorry or beta, and then you can just do a De Morgan's, and what you'll get is um, alpha and not beta, right? So this is just material implication, and this is De Morgan's, and then you get this. So it's a very like two-step proof, very easy proof. Do you have any questions about that?
Uh, so far, I haven't done like a material implication with something in brackets directly. Would there be a missing step somewhere, such as would if we were doing it longhand, would we need to first like multiply out the negative So would it be like not alpha implies not beta, and then do the material implication on that?
Wait 1 second. I don't get you. Are you asking me if like there's a longer way to do it?
Yeah, because normally material implication is alpha implies beta,
Right.
and here uh we have something on the outside.
Yeah.
So
Not. Uh. Let me
so
see.
could I multiply out and do not alpha implies not beta, and then do the material implication on that?
No. Are you asking me if you can do this? Like alpha implies not alpha implies not beta?
Yeah, and then
No,
do
that
the
wouldn't
material
work. That wouldn't work. Um, and let's,
cannot multiply out. It's
yeah,
not like algebra.
yeah, not really. Yeah, not at least not this. Because this is actually the same as not beta implies not alpha.
Yeah, contrapositive.
Contrapositive, exactly, right? Uh, but if you multiply this, what do you get?
Then you get if you multiply what, sorry?
If you multiply this, what will you get?
I don't think we've done multiplying out conditionals yet.
Yeah, so let's try um okay. So let's say you want to see if this is a valid um you know, not,
Conclusion.
yeah. Okay. So yeah, how would you go about doing this proof?
Well, we could do indirect proof, or we could just draw out a truth. I think truth table would be easier, right?
Truth table will be easier, yes. Um
So then,
yeah, so let's draw
then
alpha, let's draw beta, um, true, 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 false, false, true, false, false. Okay. So so you have alpha implies beta. So that's true, false, true, true. Um, then you have the opposite of that. Um,
yeah,
which is not alpha implies beta, and
so
that would
then
be
false, true, false, false.
false, false, and
And
then
then we need not a column for not alpha, right? And column for not beta.
yeah, or we can just directly um, do it.
So false, false is true.
Mm-hmm.
And then here, false, true is true.
So this is, yeah, false true is true.
True, false is false.
True false is false.
True, true, true.
It's true. Yeah. So
They're not the same.
they're not the same, right?
So it's not a valid rule then. Or not, I don't know. It's
They're
not
not
yeah,
equivalent.
not equivalent, yeah.
Yeah, this is not equivalent to this. So basically, yeah, this is not equivalent to this.
But I can use the rule inside the brackets.
Yes, you can use the rule inside the brackets.
Cool.
Remember we used the rules inside the bracket even the last time when we were doing the proof for hypothetical syllogism, where we created a conditional and then we did a modus ponens. Remember?
Yeah.
Let me zoom out and go there. Yeah, over here. Was it here?
Mm, I think it was before that somewhere on the left, maybe.
Yeah, somewhere. But yeah, we have definitely done replacements inside. Anyway, but yeah,
Conditional proof. Just to recap, it's when you assume the first variable, right?
you
Is that
yeah yes, you assume the antecedent and you try to reach the consequent. Um, but it doesn't have to be just one. You can have like multiple assumptions in the proof. Yeah, we'll get to conditional proof next time. But yeah, actually not next time. Maybe later. But yeah, like yeah, you can't multiply um, multiply this like that. Yeah, yeah. Anyway, um, okay. So back to this proof.
back to doing the well, yeah, the proof for the negated conditional.
Yes,
So then we do the what did we say? We do the material implication inside the brackets.
yes,
So negative, negated alpha or beta. And then De Morgan's law, you said?
yep.
Then it's alpha and not beta.
And we have what we wanted to show. That's what we wanted to show,
You-
right?
Yeah.
Yeah. So that's just the proof for negated conditionals. This is like really useful. And this also gives like an understanding of what it means for for a conditional to be false. So whenever somebody like let's say you give somebody an argument p implies q, p
Yeah.
therefore q, right? If somebody says I reject p1, okay, you can just ask them, okay, do you think you are not convinced of p1 or do you think p1 is false? Because if they say p1 is false, they are affirming this. They are affirming p and not q, and then you can just push them for an argument for p and q. Um, so that's just like an idea. So the next one.
So could you give an example, maybe in like real words, or how it would be like in a real life situation? For
I'll
example,
have to think about it.
for example, for example, if someone says the argument just completely ridiculous, well, not an argument, a proposition, like if the sky is blue, then the sky is green. Can you just outright reject that?
If the sky is blue, then the sky is green.
Yeah.
Um, sure, I guess. Um, so if you have like sky is blue, implies the sky is green.
Because you could just ask, if I understood correctly, what is the argument for that, right?
Yeah.
Or
Or you can just move for like move to falsify as well. But that'll be like like it could be like empirical, like you could be like, look, the sky is blue, but it is not green. So you could just drag someone outside and show them that the sky is blue and the sky is not green, and you will have falsified this. So
Hmm.
you don't just
So
have
you
to
just
like,
need,
yeah,
so you need to find a case of it just not happening.
yeah, something like that. So yeah, I mean, in this case, it was an empirical thing where you could just show people that, um, and you can also have something like, yeah, that will be a bit controversial. So I don't want to say that. So anyway, yeah, forget it. But yeah, you can just like in this case, you could just drag them and show them that. Um, yeah. Anyway.
But say if someone came up with that argument, like if the sky is if the sky is blue, then the sky is green. The sky is blue, therefore the sky is green,
Mm-hmm.
right? Like in the argument, like uh,
Yeah. So let me
like
just write it down. So sky is blue implies um, sky is green. Sky is blue. Therefore, um, sky is green. Okay. So it's simple. Like, how would you evaluate this proposition? You will look outside and you'll be like, okay,
yeah,
this is true. You look outside and then you'll be like, okay, this is false. If this is true and this is false, this is false. So you rejected P1 and you've declared the argument unsound.
okay. Um, and what about if it's something someone says something like if the if the sea is blue, then the sky is blue.
If the sea is blue, then the sky is blue. What were you asking?
Because these are like two things which are sort of correlated with each other, right? But it's not like one causes the other one.
I don't get you. What? Uh, oh, one sec. Uh, okay. Let's see. So, if sky, if sea is blue, then sky is blue.
Yeah.
Oh, yeah, yeah. I mean, um, under like if you're using a material conditional, you would just evaluate the same thing. You would look at the sea, you look at the color, and you'll be like, okay, it's blue. Yeah, fair enough. You look at the sky, you'll evaluate the propositional. You evaluate the truth value for this proposition. Okay, it is blue. Then yeah, like this conditional is true. That's how you would evaluate
The
it.
condition. Yeah. But it doesn't necessarily mean that one causes the other one, right?
Yes, the material conditional does not talk about like a causal relation. Uh,
Okay, this is what I was trying to understand. Yeah.
right. So if you want to, you know, um, get like a causal kind of thing, there are like non-classical logics that deal with like that are like relevance logic, which kind of require that there be some kind of like a, you know, a relation between. But the thing is, when, you know, as I said before, like whenever we are evaluating um, the truth value of alpha and beta, we don't bother to look for a relation between alpha and beta. We just look at alpha being true. We just check if alpha is true. We just check if beta is true, we put the truth values into the truth table, and whatever the output is, that is the truth value of this proposition. So that's how we should be treating the material conditional as well. And if you want like something um, that's like causal in nature, maybe you can have like a relevance logic or something like that, or maybe even within deductive logic you can have like some kind of like probabilities associated with this, and then that's how you do it or something like that.
Okay, yeah, because this was also I wasn't too sure if if this implication is a causal thing, you know.
Right. Like it just happens to, so if like it just happens to be that in this case like a causal relation is also true on a material conditional interpretation. um, like for example, like if you want to say something like saturated fat intake um, causes if you consume saturated fat intake, then sorry, wait, what am I saying? Where's my grammar? So if I say increase in saturated fat intake, right? um, so if you increase your saturated fat intake, um, then you will, you'll have cardiovascular disease, so like ASCVD risk.
Oh yeah, increased risk.
Right. um, Increased risk of ASCVD, and this is like a causal kind of thing. um, and in this case again, you can either take, like, you can just evaluate this. Okay, yeah, there is an increased saturated fat intake, and then you can be like, yeah, there is an increased risk, and then yeah, the conditional happens to be true in this case. But it's the like it's a causal association, but the material conditional does not talk about causal associations. Like there's no like relation between um, uh, the antecedent and the consequent beyond just being connected by a conditional.
Mhm.
Yeah. Okay.
So, but could someone call the conditional into question?
Like which conditional?
So if someone has a conditional, you know, could someone
Mm-hmm.
say what's the argument for this implication?
Yeah. Yeah, you can absolutely. And like there are proof strategies. Like for example, let's say there's some argument P implies Q, P therefore Q. Okay. um, and then I call this into question. Then you can be like, okay, here's an argument: S implies P and Q. S therefore P implies Q. So let's say I was like, okay, what's the argument for this? uh, you can be like, okay, um, not S implies P implies Q implies S and not P implies Q. Not S and P, sorry, not P implies Q. Um, Therefore, um, S implies P implies Q. Something like that. So basically, yeah, you can have like some argument tree which, um, you know, there's like conditionals all the way down, and you're trying to prove conditionals. Um, and then maybe there's like like some proposition which is sort of like empirical, and that's how you get it.
So normally the when it's getting called into question, there will be some sort of causal claim or something like this.
Yeah,
If
it
someone called.
depends. It depends on the claim. Sometimes it could be a causal. Sometimes it could be a causal. Um, we don't know. Yeah, it depends on the context.
Okay.
Yeah.
Yes, in the book, some of the when you're translating the text, it's like long paragraphs, and it just when I read it, the words in English, it seems a little bit like gibberish. Some of it,
Oh, which
because it's
ones?
just like just the arguments. For example, the exercise 3.4.
Oh, one sec. Exercise 3.4. Yeah. Oh, this one. Concept of self is irreducible. Um,
Or some, yeah.
yeah, I know. Yeah.
So, so for example, when you see these, can you directly understand exactly what's going on now that you're well versed with prop logic?
So I know that there is an ostensible argument form here. Like I can, so I know that anything between if and this comma is one proposition. So there I'll be like, okay, there is a self. It's one ostensible proposition. The concept of self is irreducible. That's another ostensible proposition. So I'll just write them down in like a form. Um, in a way that it's an ostensible argument. Like it's not clear to me that it's an argument at this point, but maybe once I get clarity on what those premises mean, what concepts they are invoking, then they are propositional. So I just know I know what's happening in like the structure. I know what's the structure, but I'm like I wouldn't be convinced that this is an argument until I'm like given semantic analysis. Um, and once I have like semantic analysis of that, I understand the propositions, understand the premises, and I understand the conclusion. Then I'll be like, okay, this is an argument, and then I'll try to start evaluating the truth value, and then that's how I'll proceed.
Okay.
Yeah. Um. Anyway.
Yeah, because I'm constantly trying to think how can I apply this, you know,
Yeah.
and
Yeah. It's yeah. Okay. So the next one is what? Simplifying antecedent and consequence. I'll write A's and C's. Okay, so the first one is this like alpha. Let me. Alpha implies um, beta and gamma. Alpha um, implies beta. Is that what's yeah, that's it. So how would you prove this?
uh, could we do a material implication on it at the start?
Sure.
And then looks like we could maybe do a distribution.
Okay. So how would you do that?
So it'll be not alpha in brackets or beta and alpha or gamma. No, not alpha or gamma. Yeah, not alpha.
Okay.
Yeah.
One sec. Okay.
And then I guess we don't want gamma anymore, so we can just do a simplification on the left-hand side.
Okay. And then
And
that's
then
material multiplication.
material, yeah.
Now you can do the same thing for gamma. You can just get alpha implies beta, alpha implies gamma using the same thing, right? You can just simplify this one out
Hmm.
instead of this.
So we pick, yeah, the right-hand side.
Yeah, exactly. So I'll just expand this. I'll just write
So alpha implies beta or alpha implies, yeah.
yeah, something like that. Um, and the same thing for, you know, um, for like, if you have like alpha and beta imply something. Sorry, alpha or beta imply gamma, right? You can just get one of them. So let's try doing that.
Just before we do that one, uh, on the top, on the right-hand side, so alpha implies beta or alpha implies gamma.
Mm-hmm.
It's not possible to do a simplification on this one, right?
No,
So-
simplification only works with conjunctions. Oh, wait, what do you mean?
Because before we just had the proposition alpha implies beta, right? Well, the first time we did it,
Yeah,
and then and now we've got it connected to a alpha implies gamma using a disjunction, right?
yeah,
So based on our proof, then uh, shouldn't because normally it only works with a conjunction.
no. So the thing is, um, wait, why would it only work with a conjunction?
Simplification.
We aren't doing a
So simplification.
simplification.
But the first time, initially when we had the proof, it was alpha implies beta, right?
Yeah,
And so now we've replaced that with alpha implies beta or alpha implies gamma.
right.
So, so does that mean alpha implies beta or alpha implies gamma is the same thing as alpha implies beta? How you did it there, or am
Oh,
I missing
it's
something?
not the same. It would have the same truth value because you can just apply like an addition rule, right? So
Uh, yeah, we did addition there between. Yeah, we because we had the two um premises. We had alpha implies beta, and then we had alpha implies gamma, right? And
yeah,
then what you did was you did an addition between them, or not? No, you didn't do an
I
addition. You
didn't do an
did
addition.
a.
I just said that this entails this. It could entail this or it could entail that.
Okay,
So that's just what this means. So
but
if
yeah. Go ahead.
No, so if you if you were to apply the rules over here, you will get this. If you
Yeah,
were to apply rules over here, but with like a different focus, you would
yeah,
get this.
yeah.
So this is the same as either this or this.
But it's not the same thing as the whole thing.
Uh,
So it's not this. It's the same as alpha implies b. It's not the same thing as alpha implies beta or alpha implies gamma, right? It's either one or the other, or is it? Can you
no,
just write
in
the
this
whole?
case it'll be equivalent, right? So one sec. So this is equivalent to this, right?
Yeah,
Which means this will have the same truth table as this.
yeah,
And we also know this is equivalent to this, which means this will have the same truth table as this.
yeah.
Which and if we just do a disjunction, they are both the same truth table, so it will be P or P, so they will have the same truth table.
Okay.
So
So when you take both of them and do a disjunction, the truth table won't change.
yeah, so let's try it with this, right? P implies Q. Is the same as not P or Q, right? So you will get T F T T, and you will get T F T T over here. Now if I just do a disjunction of this and this over here, this will be true, this will be false, this will be true, and this will be true. So the disjunction of two of this and this is the same as this.
And it works also when we have three variables.
It should, right?
'Cause
Theoretically.
In the one above we had
Yeah.
gamma as well.
Yeah.
So this is like an extra rule that when you can.
Uh,
This is sort of because normally the uh, conjunction that we do is this is not a conjunction what we're doing.
no, this is a disjunction.
Yes, but it's sort of it's like what is the name of this that we're doing? Like when you put them together with a disjunction, does it have a rule
Not really.
or not really?
Yeah. I mean,
Okay.
even if you replace this with a conjunction, it'll be fine. Like, so this is the same as this. Oh no no no. I don't think so. Or I guess in this case it would be. True true true, false false false, true 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 true. Yeah, I guess in this case it'll hold. But maybe in the bigger case it might not. I'll have to check. Let's check it. One second. So, because I'm too lazy to draw the truth table, I'll just be like P. What is it? P implies Q and R. P Q and
Q
P.
P implies R, right?
Yep. Oh wait.
Let's put some brackets.
Yeah. See, it didn't tells it.
But I haven't looked at trees yet, so I don't know really
Yeah,
what's
that's
going
fine.
on there, but
Yeah, like all you need to see is that this entails this. it entails the disjunction. It also entails the conjunction.
Mhm.
So yeah, you don't need to worry about what the tree is, but you just need to look at this. Yeah, it is
Okay.
ending. Yeah. So yeah, so that's see that we just discovered a trick. um, so yeah, so we just discovered another trick, which is like not in the book. Um,
Okay.
so it's the same thing as this.
But with the same thing as on the top right, but with a conjunction, right?
Yes. Yeah, that's why I said like even if you put like a conjunction there, it's not gonna make a difference. Um, yeah. And guess what? Even if I put an implication, it's gonna work. So another trick,
How did you know that?
huh?
Could you just see it, or how did you know that?
That well, it's the previous trick that we learned, right? Not this one, this one. Um, no, not this one either. This one. So if I know something, like if the like if like the conjunction is true, then this is true. Like if alpha and beta are true, then alpha implies beta is true. So I just applied that here.
So that this was in the proof that we did for the making the conditional.
Yeah. It wasn't
Yeah.
in the proof. It's one of the tricks that we derived.
Uh,
Yeah. These are the
oh,
tricks, right?
oh yeah.
Yeah.
Oh yeah, that was the biconditional.
No, no, no. This is the making conditionals.
I mean, it's oh yeah, making. Yeah.
Yeah. So if alpha and beta are true, then alpha implies beta is true. If alpha and beta is true, then beta implies alpha is true. If alpha and beta are true, then alpha uh, and beta are true. Then you also have alpha double implies beta. But I didn't write it because this is making conditionals, not making biconditionals, you know.
Yeah.
So that's why I didn't write it. But yeah, like that's how I just figured it out on the spot. Like I just saw the and I was like, yeah, like even the implication would work. So that's basically how like you start developing an intuition and you're like, yeah, like even this is gonna work. So alpha implies beta implies gamma. A implies alpha implies gamma. Right? So yeah, like it's like once you start seeing patterns, you'll be able to figure it out like this, like how I got this, right? Um, yeah.
Okay.
I can see one more. So let's just flip this. That also works. Right? So and how did I figure that out? Because, you know, these are commutative. Conjunctions and disjunctions are commutative.
Yeah.
So if I know
So
this is true, then I know the commutation is true, and if the commutation is true, then the commutation of this is true.
yeah, so you just switch them around.
Yeah. So once you start seeing patterns, you'll start, um, developing an intuition. So yeah, we had like four tricks from this section.
From the switching antecedents
Yeah,
and consequences.
right. Even though they are not there in the, you know, in the book. Okay, so we have combining conditionals. Um, was it the fifth one or the fourth? Yeah, fifth one.
Number 5, yeah.
Yeah. Why is my computer suddenly slow? Conditionals. Now this is also pretty straightforward. If
It looks like
alpha,
it's got a long proof. In the book, it's got a long proof.
oh, okay. If alpha implies beta and gamma implies beta, oh, I should write it like this.
It's better to write it like this, right? So you can spot some patterns.
Mm-hmm. It's the same as alpha and gamma imply beta. Okay. Let's try not to use the book to prove it. We'll figure it out. And we'll see if we can do a shorter proof than what the book did.
So, I guess should we do a material implication on both, what's inside the both brackets?
Yeah, we can try that. Not alpha or beta. And not gamma or beta. Okay. So this is supposed to be one material implication. I'll just rename the step as 2.
Oh, second premise, yeah. Hmm.
What are you thinking?
well, we have two brackets,
Mm-hmm.
so I would guess then the only ones with two brackets we have is material equivalence or distribution. So I'm guessing it'll be
Yes.
distribution.
Yep. But how will you do it?
So the common one in so it's I guess we can do some just commutativity just so it's in the form.
Uh, what do you mean?
So like just so it looks a little bit better, I guess. So like line 3 open bracket beta or
But why? Because like you want beta to be in the antecedent, right? So in the consequent, right?
so I will oh yeah, we want it in the consequent.
Yeah. So what if you treat this as one and you just distribute it like this?
Okay, so then if we treat it as one, then like that, so then it will be yeah, so it would be not. So we're gonna need a lot of brackets, I think, but it's gonna be not alpha or beta, and then and not gamma, and then close. And then or
Hmm? Why?
because between the two brackets we take what's between the not gamma and the beta, right? Or
Right.
okay, so then it's not alpha or beta again. And beta. Close. So there we did a distribution. Two distribution. This one's getting a bit crazy. So we need to get a implication back.
Yep.
We do a we could do another material implication
Another material implication?
between the two brackets.
Mm, why?
I I don't know how to make our life easier, but this is the only option I can think of how to convert a disjunction.
No, 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 don't like. Yeah, like don't look at this right now.
Now I'm looking at the disjunction on
Yeah.
the third premise of between them.
Oh, this one.
Yeah.
Yeah, don't worry about it. What do we do inside?
Okay, what can we do inside? We could do a
We can distribute again, right?
possible options. Yeah, distribution. Yeah, we could distribute again.
Yeah. So
So if distributing again, it's gonna get a bit crazy. But
yeah, I'll use different colors for the brackets. Um, yeah.
so normally when we so we're expanding out the distribution, right?
Mm-hmm.
So normally when the form of the distribution is that we have the not gamma on the other side, right?
Yeah, but you can skip a step. It's fine. It'll be a bit
Yeah.
cumbersome.
Yeah. So then should I just do it like as it is? Yeah, so then not alpha and not gamma. And then between them we have an or, and then we have beta and not gamma. And then on the alpha or beta. Not alpha and beta. And then or beta and beta. Free distribution.
Oh, that whatever distribution.
So 5. Doesn't look like we can do another distribution on this, right?
Um,
This
where?
one is not distribution. I don't think this one is distribution.
Okay.
So uh, it is possible to do material implications inside the brackets, but I don't know how it would get us anything.
Um, yeah.
Um, we could do maybe another material distribution, no, another distribution
Mm-hmm. How?
by taking the bracket on the left, well, the big bracket, and multiplying it out or distributing it
Um, this one?
by taking everything there
By taking everything there and
and then doing or and then not. But we just keep on gonna go. It's like we're going on for infinity.
yeah, so the thing is, you can just get rid of these brackets.
Okay.
So you will get something like this. So this is just beta.
Oh yeah, that's the rule of what was it? Tautology.
Tautology.
Or
Yeah.
yeah, we haven't used that one yet. Then
I'll just keep the rest the same, I guess, and then just say tautology.
and then there we have a common negative negated gamma.
Right.
So we could uh, do distribution on it.
Mm, let me see. Let's try it. Okay, let's try it. I don't know.
I don't know. We've done so much that I've forgotten if we're going in the reverse direction.
Uh, we'll see. Let's see.
So then let's say, yeah, negative, negated gamma, and then in brackets,
Wait. No, hold on. There should be an easier way to do this.
so I'll cross out what I did with the gamma.
You know what? Let's start again. Screw this. Um,
So it looked like we were doing, we didn't follow the method which the book was doing. I took a brief glance.
yeah, that's fine. We'll figure it out on our own. Screw the book.
Yeah, this is independent.
Yeah, I mean, if we come up with the same proof, that's fine. But
Yeah.
but we want to like prove it ourselves. I mean, I can take the easy way out and do like an indirect proof. That should be very straightforward. But yeah, like
Yeah. I'm using reductia ad
yes,
absurdum.
yes. But that'll be an easy way out. We want to use, the rules. Anyway, so first step,
But
I guess we'll do the same thing. We'll just do a material implication.
yeah.
Oh, sorry. It's supposed to be not alpha. Why is my computer crying? Yeah, alpha or beta and not gamma or beta. Okay.
So I guess we can do take out the beta, right? Using a distribution.
Mm,
So it's like beta or not gamma and not alpha.
beta or not gamma or alpha?
Not alpha.
Wait, beta or not gamma or not alpha?
Oh, and yeah, not gamma, not alpha in brackets.
How? Well, what are you doing exactly?
Using distribution.
Okay. Which, like, are you distributing this over here?
So I'm taking out, I'm going in the other way.
Or which is?
So I'm like uh So if you rewrite it in the form so it's easier to see, so then I like
Okay.
I can do commutativity. So it's like beta or not alpha,
Not
and then
alpha. Okay.
and beta or not gamma.
Okay.
And then it's possible to, rather than go in the other way. So then it's like beta and then uh or, and then in brackets it's not alpha.
Beta or sorry, beta or
Not alpha and not gamma.
wait. How are you getting not gamma?
Because we have not gamma there on the right hand side.
Okay, but how are you moving from this to this?
So I'm doing distribution.
Okay, how like
I'm going, so we know distribution is alpha or beta and gamma is, so if we write down the distribution rule, I guess it might help.
so like
So
you're distributing this entire thing with this and this.
no, I'm taking out the beta.
You're taking out the beta.
So if you write what I've got on my page,
Yeah.
uh, boss.
Oh, you're doing a
So
reverse
then,
distribution.
yeah,
Oh, got it. They say that. Okay, okay.
I said in the other way. If
Oh,
it's
okay.
reversed,
I
then
didn't. I didn't. Okay. Yeah, yeah, yeah. Fine, fine.
I don't know. There's a correct term.
No, no, no. Yeah,
Reverse
no, no, no.
distribution.
There's no correct term, but like, okay. I didn't hear the other way. Okay.
Maybe I thought I said it, but it's not really too important. Maybe I
Yeah,
didn't say it.
yeah. It's
Maybe.
fine. It's fine. I got you. I got you. Okay. Now.
So now we can do a material implication, maybe, or
Mm-hmm.
yeah, a material implication.
Okay. We can try that.
So then beta goes to, well, beta implies
Mm-hmm.
not alpha not alpha or not gamma. Well,
Oh no.
uh,
And
oh no, I'm missing a yeah, like it should be not beta at the start.
oh yes, exactly.
Technically, we could have done like yeah, a double negation, but yeah, for time
Yeah, yeah,
we
yeah.
can
Sure.
skip.
No problem. Yeah.
Yeah. So then we can do De Morgan's law.
Um. Already, or do you want to do something else before that?
I would take out the negation and then do like a contrapositive.
Yes. So you'll do not not alpha and not gamma implies beta, right?
Yeah. To be honest, I first took out when as I was writing, I first took out the negation, but now you can do De Morgan's law.
Right. So now you'll get alpha or
And
De Morgan's, right?
gamma.
It'll flip this.
We flip. Oh yeah, we flip.
Yep. Oh wait, I think I made a mistake over here. It's supposed to be a disjunction. Alpha and beta imply alpha and beta, and alpha implies beta and gamma implies beta. Then alpha or gamma imply beta. Yeah. So yeah, that's one proof. Let's try finishing this one, and then maybe next time we'll try to do. Let's try to do the same thing over here. We'll finish this. We can
Wait,
take
was
the
this one that we were?
yeah.
This was one where because we were going sort of deeper into the distribution, right? We need to do reverse distribution.
Yeah.
So then I guess we can do reverse distribution on both of the first two brackets and the second two brackets.
But that'll give us this, right?
Oh yeah, we're just going back
Yeah.
to where we were.
Yeah, I guess. Yeah. We probably just screwed this proof. um,
But we're just gonna go back until we're in the same place of the second proof, right?
maybe. Yeah. And then yeah, and then we just do the rest of it the same. Yeah.
Yeah, I think the problem was I didn't know the word for the other reverse.
Yeah, it's fine. You could just say, yeah, it's fine. Yeah, it's fine. We'll
So
just.
normally, yeah, in the future, I know that, yeah, reverse of everything.
Yeah.
I'll just use that to make things clearer. So like reverse association or reverse distribution.
Okay. Yeah, we have this proof. I think there is one more, which is that one. So we have combined the um, like we have like common consequence, right? Now we can also have common antecedents. You can have alpha implies beta and alpha implies gamma. And then you'll get what?
Based on the book, it's alpha.
Oh, don't look at
implies-
the book. But yeah, it's alpha and gamma.
Okay, so you're just spotting the pattern.
Yes.
That's the
So check the
in the other
pattern over
one
here.
we.
So here it is like a disjunction. I just spotted a pattern and I was like, yeah, this will be a conjunction.
Okay, fair enough. So yeah,
Yeah.
so yeah, in the first one we're taking the antecedents, right? And then they're in the two antecedents become the a conjunction in the antecedent of the consequent of the
Yes.
implication. Sorry, not
Yes.
consequent, implication. And then in the second one, we're taking the two consequents, making conjunction, and then that's the consequent.
Yeah. Yeah.
Cool.
I think the last one is also like not. It's pretty easy, so we'll cover that and we'll call it a day.
Yeah. But you want to? You mean we'll cover the next one now or
Yeah, it's
another
very
day?
short. It's not very.
Okay.
Yeah. If something entails its own negation, then it is false. That's all it is. Oh wait. So if alpha implies not alpha, then it is false. That's all it means. Um,
Alpha implies. So it basically means that the consequent is you're taking the consequent of the if something entails its negation, then you just can write it's equivalent to the negation.
yeah. So you can prove this as well. So you have, let's say, alpha implies not beta. Come on. Sorry, not alpha. You can just do a material implication and that'll be not alpha. This is a very easy proof. Or not alpha. And then you just do a tautology and you get not alpha. That's all.
Cool.
Yeah. But I don't
So
think you'll ever like this is probably something that's hardly ever used in proofs. Yeah. So yeah, those were just a few tricks. If I think there are a few more tricks that I use, but I can't think of them off the top of my head. So if I recollect some of them, I'll tell you in like future sessions. Um, like really neat tricks. Um, but yeah, I think it's been enough practice for today.
quite quite a long one, yeah.
Yeah. Okay. So I guess next time we'll talk about the biconditional rules, and we'll also talk about um,
Explosion maybe at the
explosion.
start.
Yeah, that's in the book. Yeah.
Thank you.
Yeah. No problem. So we'll catch up next week and continue. Yeah. I'll end the recording then.